Okay, so we are moving on to rational exponents today. It's going to be a wild ride. That I proclaim that's going to be a wild ride? Okay. So we're going to work on converting between radical and exponential form. We're going to apply the properties of exponents and corresponding properties of radicals that we're learning. And we're going to evaluate exponential expressions. There's kind of a lot going on. All right, so in Algebra 1, you discovered that the properties of exponents apply to all integers. And these properties also apply to fractional exponents. So it says if we've got this 1 over x squared, and that quantity is squared, okay? That's the same thing as saying x to the power of 1/2 times 2. Where's the 1/2 come from? Like, where can you see that? The fraction, okay? Like, here's the 1 and the 2, and so we just leave it as a fraction. It's like we take the x out, okay? All right, so then that means, though, what's 1/2 times 2? So this is the same thing as x to the power of 1, which we just write as x. Yes, you can have fractional exponents, and that is what we're working with today, our fractional exponents. Okay. My calculator says error, and I agree. Well, you just coded it into your calculator wrong. It doesn't say error. It likes fractional exponents. Okay, so then we have this therefore. Okay, if we have 1 over x squared, that's the same thing as the square root of x. Now, the cool part about this that makes sense, okay, is we don't write in the square root with a radical, we don't write the index, right, the 2. But there is, in a square root, the index is 2. What's the power on this x? Yeah, right? Like, we keep the power here in the numerator, okay? That becomes, or so like the exponent here becomes the index. And then we keep the power that's there to the power of 1, which is what they're saying here in general. All of this, so it's saying, well, 1 over x to the n power, it doesn't matter if it's a 3, if it's a 5, if it's a 12, is the same thing as the nth root of x. So again, I'm trying to help you see, right? The exponent becomes the index, okay? And the x, well, I don't want pink. The x was in the denominator, and now it's under the radical sign. Okay, so noticing those positions. Okay. All right. I'm kind of front loading all this information. We're going to come back and use it, but I think it helps to front load it a little bit. Okay, so the next one says recognizing that x to the m over n power equals. So I've kind of run out of room. Let me erase this one so I can use that space. Okay, so we're saying x to the m over n power equals. We could say, well, that's the same thing as x to the m power times 1 over n. So there's because m times 1n is going to be m over n. It's kind of like the opposite of what we did here.
Oh, because it's okay. I'm like, didn't you do that wrong? But it's different.
It's kind of the opposite. We're taking it back. Okay. So we could also say that then this is equal to we can switch these because of like the commutative property. We can switch places here and say, well, this is the same thing as x to the 1 over n times m.
So flip-flop?
Yep, you can flip-flop those. Okay, these two can be switched around. Okay, we can move them back and forth inside there. But again, it goes back to the commutative property because, yes, because when we have a power raised to the power, we multiply the two together. So then because we're multiplying those numbers, they can be switched. Huh? Doesn't really matter where they are. You got it. Okay. But that leads us to this rational exponent definition that we're going to use. Okay, so if the nth root of x is real and m is an integer, so this idea, either of these works. Now, and it's the same thing as here. Either of those works. Well, we've taken this, sorry, I shouldn't say it's the same. We've taken that and put it into the radical form. So we said, okay, well, x to the m over n is the same thing as if I take the index, okay, I put the n in my index and have x to the power of m, which means I'm going to evaluate the power first. So I have to solve this value, and then I find the radical of it, the radicand. Or, but you can't. Or we can take our index, and we can evaluate the root, so we can find, the square root of x, the cube root of x, and then we can apply the m after we do that. Either way, we're going to get the same answer.
So there's 25 different ways of doing the same thing.
Not 25, but close.
Too many.
Several. We'll go with several ways. Okay, so let's dive in. Now that we've got, like I said, now that I've front-loaded all this information, let's actually apply all of it. We're going to apply it a little bit at a time. Right? We'll come back to it. Okay, so 16. Or, sorry, 16. 1a there, actually. So we've got 16 to the 1/4. We want to evaluate each exponential expression. So we can do that if we can put it...
You're just dividing?
I'm not dividing.
16 by 4?
But well, you're not dividing it by a 4th. Right.
But this is different than just multiplying to the power, which I'm not sure.
Wouldn't it be multiplying it?
Because if you divide by a 4th, you'd actually get a bigger number.
Wouldn't it be? So the answer is not 64.
No. Okay. So remember, like in this case, the denominator becomes your index. So this is going to be a 4 because your denominator was a 4. Okay, it's a weird 4, but I was trying to copy it, but I didn't quite get it.
Would it be like, so with whole numbers, you're just multiplying it by itself? With the 4th, would it be like multiplying 16 by a 4th of 16, which would be what, 4?
16 times a 4th would be 4, but that's not your answer. Because it's...
No, I don't mean 16 times a 4th. 16 times whatever a 4th of 16 is.
A 4th of 16 is 4.
Yeah, so if that's 4, then wouldn't it be like 16 times 4?
Yeah, which would be 64, which is what he was saying, but that's not what it is.
Okay.
Yes. There you go. Here's some more calculator. Okay, so let's take it back a second. Okay, so the fractional exponent is actually a square root. Okay, so the denominator, the 4, tells us what the index is, and then we put the 16 in here. So we're finding the 4th root of 16.
So just gotta divide it again by primes.
You can do division by primes. Yep, like 16, if we divide it by 2 is 8. Divide by 2 is 4. Divide by 2 is 2. Hey, wait, there's 4 2's. So the 4th root of 16 equals 2. Okay. B and C, the thing I want you to look at here is our negative sign. Okay, here in B, our negative is out front. the exponent is not included. In C, the negative is inside the parentheses, so it is included with our exponent. Okay. All right, so then what is my index on this root? So I'm going to have the negative out here. Yeah, but I want to know how we're set it up. You push buttons on a calculator, it's true. But what did you put in your calculator? Did you do negative 125 to the power of 1 over 3? What did you put in your calculator? And you put the cube root of it? See, that's what I want. You want, okay, so see, but you do know what I'm asking. So you did the cube root of 125. And you got negative 5 as your answer.
Just throw out the negative to the left side, 'cause that's good.
Right, because it's not in there. The exponent only applies to what's directly in front of it. Okay, except in this one, the parentheses say, hey, the negative's included.
So it's going to be imaginary.
Ah, that's going to be imaginary. Good. So what's my index on this one?
Well, it's imaginary, so we can think of whatever.
Not for the index.
It's 2.
You wish. Just because it's imaginary doesn't mean everything about it's imaginary. So it's a 2. And the negative 9 goes in here, which would equal 3i. Perfect. If only. That was good, you guys. Even with all your banter and conversation. Okay. Example 2. It says, if I could read, evaluate 4 to the 3 over 2 power. Evaluate the power first, then again evaluating the root first. This is not hard. It just sounds weird. Okay? This goes back to the rational exponent definition. So there's 2 different ways to set it up. So what's my index? 2. And what goes inside here? 4 to the power of 3. Okay. In this case, I'm going to do my power first because everything is underneath here. I have to solve the power first. So what is 4 to the third?
It's 32. No. 4 times 64.
64. Okay, so I'm going to go ahead. So I've got the square root. I'm writing the 2 so you guys see where it comes from. You do not have to write the 2 when it's a square root, but I want you to see like, oh, it's 2, it's 2, it's 2. Okay, so now we want the square root of 64. Done. Okay, so if we do the root first, the only thing that's different, it's still 4 over the, or 4 raised to the power of 3 over 2. So what's my index for the radical? 2. The only difference is this time I'm just going to do 2 and have the 4 inside. And then I'm going to put the 3 outside instead of underneath.
So you do the inside and then keep it. Why do you do
Because I just want to prove to you that it's the exact same. That's all I want to do. But in this case, because we just talked about it, doesn't matter, right? With that definition, which one you do first. So what's the square root of 4? 2. So this equals 2 to the power of 3. What's 2 to the power of 3? 8. It does not matter which way you do it. So if you would rather, like if there's a number in here that you would rather be like, ooh, I'd rather do the square root of 4 and then cube that, then do it. Or if you're like, oh, well, I know 4 cubed is 64, then, right. So like if you don't have a calculator especially, you can do either way. Like if it had a 9 in there and it was 9, if it was 9 to the power of 4, well, I don't know about you, but I definitely don't want to have to do 9 to the power of 4 and then come back and find the cube root of it. I'd rather, or the square root of it, I'd rather find the square root of 9, which is 3, and then do 3 to the power of 4.
I can just
right.
put in the square root of 4 to the third. And it'll just tell me the answer.
The square root of 4 to, yeah,
I can just do that.
as long as you use the parentheses to say 4 to the third goes together. Good. You got it. All right. Example 3. I think I need a little bit more room. I don't have much more room on the bottom anyway, but we'll get a little bit. Okay, so we want to convert. Okay. It's true. I was like, I usually do that, but I say I'll kind of keep what I have, but we'll get rid of it. Okay, so we want to convert the fourth root of 75a cubed b to exponential. Okay, exponential means I want it to have an exponent, right? The root word of exponential is exponent. Right, but it also has the radical, so we want to get rid of the radical. Okay. So this is going to be 75 to the 1 over 4.
Oh yeah, because the cube is with the a, so then it would be a to the 1/3.
No, a to the third, so it's going to be 3 divided by 4. No, because 4 is your index.
Okay, so then the next one's
And then it's just
one
b
over 4.
To the 1/4. Okay, now the deal with this is we can't leave the 75 like this because it needs to be to this exponent that we have. So I would have started it a little bit differently. What you did was not wrong. It just would have it might have been a little bit easier if we would have said, okay, well 75, right? Because we want to get it in a simplified form. And since we have a root, that means we need to go back to prime factorization. So 75, let's divide by 5. You get 15. Divide by 5. You get 3. Okay, now the reason I say this might be a little easier to start this way is, let me go back. So we've got the fourth root of 5 squared times 3. Are you with me? Okay. Okay, and then it's times the a cubed b. The only reason I say it might have been easier to simplify first and to get that in that prime factorization is because now we could say, all right, well, this is 5 to the 2 divided by 4 power times 3 to the 1 over 4 times a to the 3 over 4 and b to the 1 over 4.
That makes it worse. What's the difference? Like, why do that? What's the point in doing that? It's just more math to get basically the same answer.
Okay, to say it's easier because it's smaller numbers for each one. We don't have a big 75 in there.
I was like, it is, yeah, like it is getting you smaller numbers. And then also to show you, like some of this is to show, like, so one, it is smaller numbers, you're getting as close. Because when we say, like if you were to simplify, and so that's where this one is a bit of a struggle with the directions. Like if it said to simplify the square root of 75, you would have to do that, or the fourth root of 75. However, this one doesn't say simplify and convert. It does just say convert. So I'm saying, like, I understand why you did this one, like the 75 to the 1/4. But if we were to simplify and convert, we would need to take it on down. Does that make sense? So I'm showing you the simplified conversion. Now, the other thing about this is if you look at this, can any of those exponents be simplified any further? Yeah, this 2/4. So you would also want to do that. So then we would have 5 to the 1/2 times 3 to the 1/4 times a to the 3/4 times b to the 1/4. Say that again. Well, 2/4 is equivalent to 1/2. Put it in your calculator.
It's not a fraction anymore. It's the same. It's telling you what numbers to multiply and divide by. And if you change those, you're going to get a different answer.
It's not telling me what numbers to multiply. Like, okay, so like, but if one, you could put it in your calculator, but two, we can try it here. So 5, this is the fourth root of 5 squared, and this is the square root of 5. Put those in your calculator, see what you get. Because I get that it seems like those are going to be different things. Because this is also equal to, so we could say the 4th root of 25.
I don't know that I put that in right. Did I put that in right?
The 4th root of 5 squared. Yeah. And then what's the square root of 5? So you got 2.2 something?
Yeah, 2.236067977. So the square root, and then the other one was 2.236067977.
They're the same thing. So again, like if we are, this is why I said like, this is okay. I can totally understand why you did the 75 to convert it. But if we were also to simplify it, then you would have to take the number down into the primes.
So we're gonna have to do that. That's just showing us how to do it.
The book has you do it, but I'm not saying like, yeah, technically, if I said convert, I wouldn't expect you to convert and simplify. Yeah. My language versus the textbook's language. Okay, so on B, we're going to actually convert the exponential form to radical form this time. Okay, so now we want it in the radical form. The key here is to express your fractional exponents using the least common denominator. So if we look here, we have a 5, and a 2. We can't put one radical under there if they don't have the same denominator. So we've got to get them to have the same denominator. Do what?
I was just gonna say I couldn't see what you.
Yeah, you're good.
So it's gonna be what, 5?
So if we have a denominator of 5, 5, and 2, what's the least common denominator that they share? 10. So we're going to write those to be equivalent. So 2 and 3/5 is equivalent to how many tenths? So 6/10. Because we multiplied both of them by 2. 3/5 is equal to 6/10. Okay. So then x, it's 4/5, so we're going to multiply by 2. So I heard 8/10. Okay. And then our y is 1/2. We multiply it by 5. So 1 times 5 is 5, 2 times 10, or 2 times 5 is 10. Okay, now that we have the same denominator, because the denominator is the index, okay, we can say, okay, now we can write these in radical form. So it's going to be 2 to the 6th, x to the 8th, y to the 5th. And then 2 to the 6th we can simplify. Like, what is 2 to the 6th? We'd rather do the math on the numbers that we can.
64.
All right, so this is going to be the 10th root of 64x to the 8th, y to the 5th. And we can't do anything else. You're right. We got it in radical form. Check.
This is like a 10th root of 64.
There is not. You're good.
I don't think we could divide by 2 enough times to get 10.
Oh, we can on some of them.
64.
Not from 64. All right, so example 4. We want to simplify each exponential expression. So I've got a couple clues here to help you. We want to factor any coefficients, apply the power property of exponents, and simplify. Okay, so we did 75, or hold on, I'm looking at the wrong problem. Okay, So one thing, let's look here. What's up with this exponent?
It's not a fraction.
It's a decimal, not a fraction. Can we write that as a fraction? 1.5 would be what fraction?
3 halves.
3/2. Okay, so that would be better if we said, well, this is equivalent to 3/2. Okay. All right. Okay, so first step, factor any coefficients. Well, we have a coefficient of 36. So what is 36 factored?
Factored by what?
Well, that's a good question. No, I like that. I like that. He says factored by what? That's actually a good question to ask yourself, because since we said, well, this is the same thing as a 2, can you find, is there a square root to 36?
Well, yeah, 6 times 6 is what I
Okay.
said.
All right. So it would be helpful if you had wrote it as 6 squared. Okay.
6 squared.
Okay. Because then we're going to distribute, because then this is going to be times 3/2, right? Because this goes to each part.
Yeah, but can we not divide all exponents by 2? Since they all have a common
Hold on, we're going to get there. Yep, I'm going to show it. So then we have a to the 6th times 3/2. And then I have b to the 12th. Oh, my color didn't change like I wanted it to. So let me go back. Okay, then I have, my board is just refusing. There we go. So then I have b to the 12th, and again, times 3/2. Okay. The reason that was a good question that Ethan asked, like, what are we dividing by? Or like, what exponent do we want? Because check it out. The 2's would cancel, and that would leave us with 6 to the power of 3.
Wait, I have a small question.
Uh-huh.
So even though that does work, what I was thinking is since we have 6 to the power of 2, a to the power of 6, b to the power of 12, all of those are within the parentheses.
Mm-hmm.
All of those can be reduced, right?
Yeah, that's what we're going to do.
But you're doing it
Because,
in a different way than I was thinking.
okay. Well, like 6 and 2, right? They can both be divided by 2. So this would be 1. 6 would become 3. 3 times 3 is
9.
9. So we'd have a to the 9th. And then 12 times 3/2, they could, all the 2's would cancel, so this would become 6. 6 times 3 is,
Wait,
yeah.
6 times 3? Oh,
Uh-huh.
18.
Yeah, is 18.
I was thinking 6 to the power of 3.
Nope, because these are the exponents, yeah. So it's like we're doing like multiple math problems all at one time.
I guess you're doing what I was, well, hang on. Because I was reducing them, so if you had left it written as 6 squared times a to the 6th times b to the 12th in parentheses, and all
Mhm.
that's multiplied by 3/2.
Mhm.
Can you not reduce just within the parentheses? Like, so divide all of it by 2 or something, to where then you get rid of the 36 squared, turns into a to the 3rd, b to the 6th. I was just thinking about going about it a different way. In this case, it works out the same, but if our 1.5 was technically like 2.
So hold on just a second. I just want to see. So you're dividing it by 2, so you're getting 6 to the power of 1, a to the power of 3, b to the power of 6, and then you're going to go back and cube that?
Is that what you'd have to do?
Yes.
Okay, so it wouldn't still be 3/2. You'd have to divide everything by.
Yeah.
Wait. You divide within the parentheses and then multiply?
Well, because
it out?
well, you said you divided them by 2, so that's where this fraction came from. Like we divided each of those by 2, and then we'd have to leave. You haven't done anything with the 3 yet, so you'd have to go back and cube it.
Exponents just get multiplied together, so that would still work. So it would still be 6 to the 3rd, a to the 9th.
Yeah, because then you would multiply. Because this is an exponent raised to another power, and so yeah, so it'd be 6 to the cubed, a to the 9th, and b to the 18th still. Yeah.
Will it work like that every time? Or you can do it either way?
Yeah. Okay, but we're still not quite done here because of the 6 cubed. So what would 6 cubed be?
Hold on a second.
Let me get my calculator out.
156?
260.
216.
Hang on. Wait. 36 is 36.
Oh, a to the 9th, I'm sorry.
Oh, yeah, wow.
Now, the other thing, and I know, like, this is one of those things, like, that, I'll be honest, I don't do well.
All of that is divisible by 9.
Cool. All of this, no, just because it can be, but we don't know what A is
No, I mean like,
or B.
well, can we not divide 216 and then the 9th exponent and then 18? So
Mm-mm.
it's 24A to the second.
Uh-uh. Nope. Okay. The thing that I'm also not good about, and so, but I'm going to point it out to you guys, and maybe you'll be better about it than I am, is the fact that right here we had an even exponent that shifted to an odd exponent.
Absolute value.
So it should have the absolute value around it.
I don't know when to do that, because I swear I've seen it other times when it's an odd exponent and we don't. So, like, when do we put the absolute value when it's an odd, and when don't we? So we also should put an absolute value over there when it was 6 to the 3rd, correct?
Nope, because it's a number, not a not a.
Okay, so it has to be a variable.
It's when it's a variable and when it goes from an even to an odd, that, and we're doing multiplication and division with it. But again, I'm not good at it. I never remember to do it, and I just know, like, if they give me a value and I get some negative number, I'm like, oh, it's not supposed to be. I know that in my head, so I don't ever put the absolute value. So it won't be on your test. I'm just going to tell you right now, like, I'm not going to grade you that on your test because I personally suck at it as well. Okay, but I am going to point it out to you so that you can do better than I do. Or like, you'd be like, oh yeah, my teacher told me about that. She sucked at it. She was really terrible about using it. But I have seen it. Okay, so when you get to college, you can be like, oh yeah, I've seen that before. Okay, I got this. I don't know what it's for, but I've seen it. Okay, so.
You can say that about a lot of things.
For Washington, you can do this thing called running start, where you can do all college classes your junior and senior year. So next year I'm gonna do all college classes, and I'm probably gonna have to do algebra again.
Oh, good luck with that. Okay, so then let's look at B. How would we do B? Let's see. Actually, yeah. Let's. I have a feeling B may take longer than our 3 minutes, so let's stop there for today.